Hello, everyone. Welcome to the sixth session of the MIA Academy. For those who are new here, the MIA Academy was an initiative started by the young water professionals of the uh, International Water Association Modeling and Integrated Assessment Specialist Group to support other YWPs in their learning of modeling fundamentals. Um, we have had five sessions so far. This is the sixth, and all the sessions have been recorded and on our YouTube channel. Um, this session today is on model calibration, validation, and evaluation. And who's better to give this session than the man who wrote the guidelines himself? Uh, Live, floor is yours.
Yeah, thanks for the introduction. My name is Leif Rieger, as Amor had mentioned. I'm the global principal for digital wastewater process controls at Jacobs. But what I'm talking about today is mainly based on my work with the Good Modeling Practice task group. Yeah, just to start my presentation on model calibration and validation. Just to highlight that calibration validation is not a separate topic, but the way I describe it is basically in the context of the Good Modeling Practice task group. So we wrote that scientific technical report in the top right corner, guidelines for using activated sludge models, and I would say it's still a good source for information. So if you want to read up on this a little bit more, there's also further reading recommendations. It might be a bit outdated, so it's a while ago that we published that, but I think most things are still up to date. Okay, so what you see here highlighted in red, that's the calibration validation step, but really it's the fourth step out of five. And the way we define calibration validation means that we shifted a lot of the effort, a lot of people would still see under calibration into step two, data collection reconciliation. Basically, if you have good data, the calibration validation step becomes a minor step, actually. And then similarly important is the plant model setup, right? So just capturing the information of the real system in your model. Okay, so I start with a definition. So that's typical. I think that's the simplest definition, and I like simple, I have to admit, of calibration. And it says iterative adjustment of selected model parameters to reach an agreement between simulated and measured values. Okay, so the first pitch I want to make is data quality. And that will be repeated throughout the presentation. So sorry for bothering you with data quality, but that is really then the driving thing here. So if you didn't correct your data, so you're using wrong data and you are trying to fit a model. So I'm not calling that calibration. So you're fitting a model somehow to bad data, you're losing your predictive power. And just to highlight that, there are so many parameters in these models that you can do that, right? So you can tweak a model to actually follow wrong data. Yeah, so that is quite important to understand. So in the context of the good modeling practice work, we prefer that you return to previous steps. So that means data collection and reconciliation, so the data part, or the plant model setup. So that is basically reflecting the tanks and the mass flows of the real system. And we prefer that over tweaking biokinetic parameters. So that is quite important to understand. We don't see data changes as part of the calibration. So if you realize something is wrong, and typically if you start, so in the calibration step, it's the first time you really dig deeper and try to understand why your model is not fitting your data, right? And that then you typically will get additional indicators that something is missing, right? And it's much better to go back to that step on data to say, okay, so something is not right. Let's make sure that the data is correct as a first step. And the same with the plan model setup. So before you touch biokinetic parameters, if at all, make sure that these two other steps are properly done. So this is also from the scientific report here. I don't go through every single line here, just on the left-hand side, the major steps. You should start with refining your stop criteria. So the original stop criteria should have been defined in the project definition. But typically, if you go through your data, you realize, oh, the data is so bad, I cannot really achieve the prediction accuracy I wanted to, right? So that's basically the difference of wishful thinking. That's what I would like to have and what is possible, right? So just because of the data, that might not be even be bad data. It could also be that the resolution is not high enough really to capture certain dynamics. Then you run the model, make sure you properly initialize the model before, and then you see there are all kinds of loops around calibration and then validation. Then you should document everything. And at the end, it's always a good idea to get stakeholder agreement, because that also forces you to properly document and explain what you did in that model, all your underlying assumptions, and maybe also the weaknesses of your model. Yeah. So and be honest with your model, and don't try to hide something from your clients. Okay, so in terms of level of effort, so that is supporting that statement that we moved a lot of the calibration work into the data portion. And you see from a relative contribution to the overall effort, we put 40% on data and only 15% on calibration validation. So what that means is, if you spend more time on getting your data right, understanding your data, reconciling your data, then the calibration validation is actually a minor effort in the overall process. Yeah, so good data, sufficiently dynamic data, that is more important than tweaking a little bit with your model performance. You should also look into, what do I want to achieve with the model, right? So that is more in consulting practice, that you say, okay, so this is the question I want to answer. And then you define how deep you have to go with your calibration efforts. So there is a clear dependency between your calibration efforts and your objectives. Okay, so now what parameters do we have, and which ones to change? Are there parameters we should change first or all at once, and so on? So just to highlight the fact that there are hundreds of parameters, there's a lot you can change. But really start with understanding your plan. Go out if you can, do a site visit, and try to talk to operators, because they will know their plan best, and they will also know how it's operated right now, right? And that, so wastewater treatment plant is a living thing, right? So it's changing all the time. It has to react to all kinds of changes in inflow load, flow distribution, the layout itself. There might be new technology, new control solutions, or there is a different permit, so that changes the operational settings as well. So if you start with your calibration, make sure that you had properly set up your plant model first. And any indication of the model not fitting your observations, that is where you should start first before you touch any biokinetic parameters. So plant model setup, operational settings, and influent characteristics, they all have a very strong effect on model predictions. And a lot of them are site-specific in nature. So if you have your tank sizes wrong, right, and that can happen, there should be as-built drawings, but somehow very often that step is dropped. So you may still have design drawings, and then during construction, things were changed. So even the tank size could be wrong. Or you put the tank depth into your model, but you should use the site water depth. So just where the water level is. And again, so that can have a huge effect on your model. Your process flows may be different, right? So maybe your recycles are not going into or in front of the mechanical treatment, or not even in front of the primaries. For whatever reason, it's dosed or recycled back to a mixing chamber right before your aeration tanks. Yeah, you have to understand that to properly model your system. So all the operational settings will change over time. And if you don't know how the plant is operated, is the RAS going from one tank to one clarifier, or is the RAS mixed and then redistributed? Are there differences in the distribution? And so on. So understanding your plant is very, very important, and don't mix that up with calibration, as I said before, but that's very important to build your model. Influent fractionation, that's the step you have to do, right? So there has been a lot of research done on what to measure, how to measure, and a lot of experience now that with certain measurements, you can just set up the influent characteristics in your model. But very often, it's still something you use in calibration. Yeah, so you have to change the influent fractionation. There are no defaults. That is certain typical ranges, but that is basically how you adjust your model to the site-specific situation. So then there are the biokinetic parameters. We have very mature models in the meantime. And the biokinetic parameters are actually quite stable, and we have experience from thousands of plants around the world, right? So we can be pretty sure that the model itself, so the standard engineering models reflect our understanding of wastewater treatment. There are new processes, of course, where you add to that, but the base processes, I would say the models are very, very mature by now. So a couple of recommendations: start with a proper model and default parameters. Right? So don't go back to ASM 1, 2, 2D, or 3. They were published in the 80s and 90s, right? So there's 30 years of experience now out there. That expertise of model building, maintaining default parameters is with the commercial simulator companies, right? And they are doing a very good job updating the models to the newest technology, and also coming up and maintaining default parameters. So if you want to model, just use a mature model and not something from academia in the 80s and 90s. Second recommendation, only change parameters. That's specifically true for the biokinetic models if you have strong evidence suggesting that that parameter value should be changed, right? And I want to see, so if I review work of my co-workers, I would always ask them, why do you think that should be changed? So make sure that you have supporting data to justify that. Some parameters are known to be very stable, so don't touch them. Be very careful. That's a funny one. So typically you would say, oh, if there are experiments out there to measure biokinetic parameters, that's the coolest thing ever, right? And at times you have to, right? But be very, very careful. These experiments are quite tricky to do. You need a lot of experience to do that. And it can go completely wrong. A friend of mine told me a story where he said he convinced a client to spend $50,000 to measure a certain parameter. And that plant decided to do it themselves, and the result was clearly completely off. And he said, yeah, sorry, I cannot use that value. That makes no sense. And the client said, well, you made us pay $50,000, so you better use that value, right? And that was a disaster then, right? So be careful. I only trust experiments if I know who did the experiments, and I trust that person to do it right. Yeah, very complex, difficult experiments. I'm not saying don't do that, but make sure that there are enough experiments that you can trust the outcome. And then classic system analysis, select parameters with large impact on the model prediction. So typically you have groups of parameters going in the same direction or highly correlated. And you should pick the one with the largest impact typically. I would reword that a little bit, that you keep the ones where you know they're quite known and stable, and change something else, but that's my preference only. At the end, what I do in review, I check if the changes, the parameter changes were done in a reasonable range. So that is my way of, so I have an idea, so what range is acceptable. If it's outside, I request additional justification. Yeah, and typically you don't have the data to support biokinetic parameter changes, right? It's rare that you have that. So that's purely based on calibration, or we can maybe call that tweaking of a parameter to get a match with your observations. Okay, so what type of biokinetic parameters do we have? So we have the original one. So that is typically what is published in the original paper. But then you see that more and more people start using that model, and you see that there are more and more applications. And after a while, if people think, oh, that model makes sense, then you will see that step by step there are new default parameters developed, right? So you have that for ASM1, ASM2D, and ASM3. There are other consensus-based parameter sets, and they are typically much, much better than the original ones. So for example, ASM3 is completely wrong. You will not be able to get proper results out with the original parameter set. But again, so there are several default parameter sets out there. If you look for these publications, make sure that the validation happened on different wastewater treatment plants, and a clear explanation on how the values were obtained for every single parameter. So there should be a long table saying we took this from this set of experiments. This is something we did ourselves. This is based on calibration and so on. If you have measurements for certain parameters, yes, you should use them because there might be something site-specific, but again, be very careful, and that should be based on properly designed experiments, checked data, and if required, reconcile data. And then the last one is if you actually iterate through, so you have no additional information, but you know you cannot fit the model, then you calibrate, and that is basically from that iteration. Also important, I saw that quite often. Don't mix and match different parameter sets, right? So you have to go back to original experimental data to say, okay, so I use that, but if somebody calibrated parameters for one model and then you think, oh, I just apply the same value for another model, that does not work. Yeah, so be careful not to mix them. Okay, let's look into the calibration procedure. Again, so the first step is to refine your stop criteria. Just a little anecdote from myself when I did my PhD. I calibrated a BioP model and I had no idea when to stop. I would probably still trying to calibrate, right, after 30 years or 20 years. So I had to ask my supervisor, and he said, "Man, I think it's good. It's good enough." So important is that you define these stop criteria before you go into your calibration, right? And you select certain target variables and you define, okay, this is the accuracy I want. If you start with your calibration step, you already went through your data and you will refine. The table here is from the GMP work. I'm not saying you have to apply exactly these numbers, but I believe we have put a lot of effort in so that you can use that as a good starting point, right? So don't switch off your brain, think that through, think about the data quality you have, think about your objectives, and then set realistic stop criteria for your target variables. Good. So then it's about, so you need proper data sets for A, calibration, and B, validation. I discussed that a little bit further later on in that presentation. Then again, make sure that you properly reconcile your data, you refine your target variables and stop criteria. And then very important, and that is not very often discussed, you have to initialize your model, right? And you can do that by running a steady state solver, but that means you're running it on the data you're using in your calibration. So if there was something else happening in front, so your plant was not in steady state, there was some kind of transition going on, then your initial point is off. Yeah, so your initial conditions could be completely wrong. So you start wrong, and how do you calibrate them, right? So achieving the right initial conditions is not that easy, and at times require quite some thinking. So let's say you properly initialize the model, maybe steady state and some dynamic simulations, and then you start your first simulation. So that is actually the first time you really look into the results and you compare your simulation results with your measured target variables. Yeah. So typically you do that in groups of parameters And important is to make sure that if you are calibrating one group and then the second one, that the second calibration step is not messing up the first one. Otherwise, you kind of have an internal loop, and then you have the second outer loop and a third outer loop. And every time you finish the outer one, you have to redo the inner one. So that is quite messy. So you have to think about what can I separate out with minimum impact on the other parameters. So this is a rough overview of what we came up with in the good modeling practice. And again, so the GMP work is consensus based, right? It's not just that there were a couple smart people doing that. We went out and talked to a lot of people to capture the industry knowledge at that time. Yeah. So important here is that you start with something which is not affecting too much of the other follow-up steps. So you typically start with sludge production, right? And that sounds, yeah, sure, sludge production, right? So that is slow and kind of seen trivial. But to be honest, if your sludge production is off, the whole model fails, right? So I recently saw a presentation on N2O modeling, and they calibrated up and down, but they couldn't even match the sludge production. So how can you assume that you can get proper results for N2O if your sludge production is not fitting, right? So that basically means the basic is wrong. Okay, so if you look into sludge production, typically you only have TSS values, right? So that means you have to understand if there's any chemical sludge produced. Yeah, so you have to understand that to make sure that your TSS includes chemical sludge. You very often change the influent characteristics, and that is mainly XU. So that's the particulate unbiodegradable fraction in the influent to increase sludge production, right? And then there's also inorganic suspended solids. I have another slide, so I repeat that in a second. And then you have wastage and effluent TSS. So the wastage is very tricky in terms of data. So the TSS measurement in the wastage stream is very difficult to measure. And also the flow is, right? And if you have intermittent wasting, then it's a total nightmare to figure that out. And then there's the question of modeling settling, right? So do you need to do that? Can you simplify that? And so on. Okay, so the next big step is nitrification. For calibration, the main thing is that you are matching DO concentration, right? But if you want to use the model later, you also have to make sure that your oxygen transfer efficiency is correct, because one of the main outcomes in design is that you want to understand how much air do I need to deliver into that zone. So that is used for diffuser distribution and also blower sizing. So, or more than that, it's also pipes and valves and so on. So very important, again, what you are targeting. Then there are aeration controls, of course, right? So for certain applications, that's what you're interested in. And then you have to model and calibrate that as well. Next step is denitrification, then BioP, and at the end, chemical precipitation. You will see that it's somehow mentioned under sludge production already. But the first one is more on the additional TSS you produce. The last one has a different target variable, right? So that is basically the phosphorus removal. Okay, so this is sludge production still. That's the influent fractionation. You all will have seen something similar to this one here, and the one highlighted in yellow, that's the unbiodegradable particulate fraction. Keep in mind, if you increase XU because you need to increase your sludge production, at the same time, you have to reduce another particulate fraction, which then would be the biodegradable part, right? So that has an impact not just on your sludge production, but also on your denitrification performance, basically. Okay, so a little bit more here. If you use, let's say ASM 1, 2, 3, there is a very rough TSS model in there. So the original implementation or the publication for ASM1 had nothing in there. So the models are COD based. What that means is there are two additional steps to get from COD to TSS, right? Realistically, you will not have total COD measurements in your sludge, right? So that is never measured, too expensive, and people may think there's limited value in doing that. And for normal plant operation, they would be right. So you need to translate COD to VSS and then VSS by adding ISS to TSS. Yeah, so that is an additional model which is often overlooked. But if your target variable for sludge production is TSS, you have to calibrate that model as well. Yeah. Keep in mind, VSS, TSS measurements are often of poor quality. Yeah. So that makes it not an easy task. So again, the ASM type models are based on COD, but your target variable is TSS. So that means you have to also understand that part of the model. My recommendation is to use a state-of-the-art model with a more advanced model for that compared to the original ASM 2 and 3 implementation. Yeah, so that basically has additional ash content calculations, and the VSS, TSS factors are all individual defined, right? So there's a lot of work been done throughout the last decades. Okay, so the next question is, do I need to model settling or just the effluent solids, right? So again, so that is part of the plant model setup to take that decision. But if you select to model settling, then you have to calibrate that settling model. Yeah. So just some simple guidelines here. If you are only interested in matching sludge production, then in most cases, it's sufficient to just set an average effluent TSS. Yeah, so that's all you need to do. And typically that's good enough. So the second one is, if you know from your data, you have a high variability of TSS in the effluent, right? So you know an average would not capture your sludge production or your inventory loss through the effluent. So then you would basically track the TSS in the effluent. And then the last one is really modeling settling. So the first two is a simple separation step, right? So a certain percentage goes off to the effluent and the rest goes into the underflow. It's a mass balance based model. The last one is to really model settling. And that is if you are interested in the performance of the clarifier. So you really want to understand how your clarifier work under different conditions. And you need a lot of data actually to calibrate the model to that. Or you want to know how your sludge inventory is moving throughout your system. Yeah, so that is when you are modeling settling. The downside of the settling model is if you calibrate that too sensitive, you may have some unexpected results that you actually are losing sludge in certain scenarios you are modeling. And if you are not recognizing that, so let's say you have a stable clarifier, but a too sensitive settling model, you're losing sludge, and then the results of your scenario are mainly driven by losing sludge. Yeah, so be a bit careful. If you use settling, you have to check how much sludge you lost through the effluent. Yeah, so very dangerous using a sensitive settling model. Okay, let's look into nitrification on the right, top right. You see the impact or the main impacting factors for nitrification. That's something typically I explain for optimization purposes, but as you can imagine, it's also very helpful for calibration. So where is a mismatch coming from, right? And that is first and foremost DO. Right? So for calibration, it's actually best to exactly follow the measured DO. However, you have to keep in mind there's a profile, right? So where you measure, so where your sensor is, that may not be representative for the whole aeration zone. Yeah, it might even be that DO is zero at the beginning of the zone, and much, much higher maybe in saturation at the end. So you have to understand the air distribution to properly model your DO profiles, right? So assuming that you can just track the measured DO is not correct in plug flow systems. Yeah, so you have to think about how low does the DO go in front of the sensors and how high it goes downstream of the sensor. So very important. And if DO actually drops to zero, there is no nitrification. So suddenly you may have a heavily reduced aerobic volume where you nitrify. And that has a bigger impact than, let's say, changing the nitrifier growth rate. Yeah, so that is typically the case if you are not reaching full nitrification capacity because you didn't model the DO profile. Yeah. Second step again, so that's calibrating oxygen transfer efficiency. And again, if you use the model in design, that is one of the main outcomes to know how much airflow you need per zone, minimum, maximum values. And then you use that in designing your blowers, pipes, valves, and diffuser distribution. In certain cases, you want to understand the process controls. So if there's anything limiting, it might be a good idea to do that at the end, because if the goal is to optimize your system, then you also have to understand how the controls work so that if you're running your scenarios, you can identify if that is linked to faulty or not properly tuned or set up controls. Alkalinity, if alkalinity is low, that may impact your model's performance. The alkalinity model is typically very rough, right? So that is something, if you realize there is a low alkalinity in your model, then compare that with measurements you may get from the plant. And that is something where you actually, it makes good sense to calibrate the alkalinity impact on nitrification if you are running into alkalinity limitations. Temperature, Make sure you understand where it's measured, right? So maybe it's in the influent or effluent or somewhere, but you actually are interested in the temperature in the tanks, right? So you may not have that in your data set. Also check if you say, oh, temperature didn't change too much, so I just set a standard temperature for that data set, but make sure that there are no sudden drops due to a storm event, for example. And then last but not least, the aerobic sludge retention time, right? So that goes back to the sludge production, but I just wanted to highlight that here again. Here it's the aerobic sludge retention time, right? Sludge production would be more the total. So DO clearly drives nitrification, but check all the other impacting factors as well. Denitrification. Denitrification is all about carbon, basically. So how much validly biodegradable COD do you have in the influent? Endogenous denitrification, hydrolysis, and then the critical one is supplemental carbon, right? So that is quite tricky. We have that quite often here in North America. If you, for example, or the plant uses methanol, you need to model a different organism, the methylotrophs, right? So that's a different performance because you still have the influent carbon, so you still need the ordinary heterotrophs, but in parallel, you are growing methylotrophs on methanol, right? And if you're using other carbon sources, you may have to change the yield, right? So you have to know exactly what type of carbon source for your supplemental carbon you have. The second one is content of your recycles. So if you recycle, there's a lot of nitrate, but at times also DO recycled back. So you can call that, or some people call that DO pollution of the anoxic zones. That is basically the internal mixed liquor recycle, bringing back DO, and then, of course, the heterotrophs like eating this oxygen more than using nitrates. So denitrification goes down. The same with nitrates, right? So if you are running out of nitrates, there is no denitrification. That might sound trivial, but in terms of calibration, that means you have to understand what is recycled back, right? So it's always a good idea to ask for some measurements of nitrate in your RAS and internal mixed liquor recycled streams. Yeah, so just to understand what comes back, right? Then there are very often unaccounted volumes, right? So you will have quite some denitrification going on in a sludge blanket, right? But there might also be a pumping station, right? So there's a big sump pump, and there's denitrification going on, right? Or there might be large channels or pipes where you think, oh, it's not really a tank, I'm not modeling that. But the size of these unaerated volumes may bring your nitrate down, which then has an impact on denitrification. And if you are modeling BioP, that is really the key. Yeah. Again, temperature is important, and then the sludge retention time as well. For BioP, there are so many models that I cannot really specify model parameters. I distinguish here three different types of BioP models. The first one is the ASM2D type, so that's the original ASM2D, or ASM3 plus but BioP module and others. And in academia, ASM2D is still widely used. The tricky bit specifically with the BioP module, in my opinion, is that PHA and polyphosphate storage and PO growth are all modeled as separate processes. And if you calibrate them individually, you are messing up the ratio between the three. So that's very dangerous. You should not touch these ratios because then the whole model loses its meaning. The second one is based on Barker and Dole. So that was a publication back in the 90s. And in fact, most engineering models in the commercial simulator still use that as a basis. Yeah. So the one advantage I see is that the polyphosphate storage and PEO growth is modeled as one process. So that ratio is fixed internally, so that makes it a bit more robust to fiddling around with parameters. The last one, the metabolic type models, they are still not really established in the field. Completely different way of setting them up. The idea is that they are more complex in the structure, but the parameters are based on first principles, so you should not touch these, right? So these parameters. So what that means for me in the consulting world is don't touch these models, right? So use proper defaults. The best you can do is using parameter sets, default parameter sets from the simulator companies, but then rather focus on the availability of VFAs and nitrates entering the anaerobic zone. So that is really the key to calibrate the models. You're not touching the inner workings of the BioP model, but you are basically calibrating them by changing the availability of a carbon source and how much nitrate they have available. Okay, so this is showing a successful calibration. It's probably the wrong example because they indeed change biokinetic parameters. I should have found one where they actually tweaked the model otherwise. But what you see is the middle red and blue ones, that was the initial run, and then they calibrated, and you see that they must have had excellent data, right? So you basically see that the model goes through nearly every single data point, right? So that is rare in consulting engineering. So what they did is they used ASM1, came up with a new default parameter set for ASM1. So it's quite some years ago now, but at the time, ASM1 was still seen as the most robust model out there. And they basically introduced newer findings and did a lot of experimental work to measure parameters for that calibration fit here. Okay, so let's go into validation. I start with a definition again. So validation should ensure the use of the planned model with the level of confidence required to meet the modeling objectives within the targeted domain of validity. So that's quite a sentence. So it's not as easy as my calibration definition. So there are a couple of points I want to highlight. So one is have the confidence, right? So you are doing a job and you want to deliver on your project objectives. And you want to do that with confidence, as of course. Then the other one is domain of validity. So that's a term you should look up maybe and try to understand that better. But what that describes is basically that the model can be used in certain conditions and in certain situations. Yeah. So you want to make sure that the model can be applied for what you want to achieve. Yeah. So the process is similar to calibration. So you apply a simulator to a new set of planned data. And the important part here is they have to cover conditions under study. Yeah? So that is the confidence piece. you should evaluate for realistic but different loading and operating conditions. And again, it's very similar to the first one, the targeted domain of validity. Yeah. So, and that sounds very theoretical, and indeed it is. Yeah. So it's not that easy to clearly identify what you should validate for, right? So that is very, very difficult to specify. Of course, you should not change parameters, and at the end, you check the model prediction quality. So the message here clearly is understand the targeted domain of validity of your model. Is there anything you have to specifically test for your application? So I think that captures it. Okay, so validation, does it make sense at all? Right, so that's critical thinking now. So how do I identify the required validation data set? Right, so what is your domain of validity? Right, so let's say you know upfront critical situation is low temperature and high temperature, right? And then you can say, okay, let's measure in winter and in the middle of summer, right? So that means you have to specify the critical conditions for your model application, right? And then the question is, do we need to wait for these critical conditions? So if your critical condition might be a heavy storm event with first flush and a huge push of the hydraulics of your plant, do we have to wait until that storm happens? Maybe it's not happening this year. Do we have to wait for next one? Or can we create critical conditions? Or even do we have to run a pilot to be able to run a model? Yeah, that doesn't really make sense because we are selling modeling as you don't need to pilot anymore. We capture everything in our model. So if you insist on validation, then probably you have to go back to piloting to make sure that you can use your model for that application. So does that make sense? Or going further, if we validated the model for an existing plant up and down, right? So we measured storm events in winter and summer and all kinds of changes, and we validated the model to death. And the first thing we do in our work is we are planning a planned upgrade. And the first step is we will demolition the whole existing activated sludge plug flow system and replace that by a biofilm or SBR. So what's left from your validation? The only thing you can claim is validated is your influent fractionation then. So does that make sense, right? So you are upgrading or rebuilding your plant. Do you need to invest in validation at all? Or what we very often do if we design not for now, we are designing for 20, 30 years down the road. So is the model still valid for these situations with changes in population, changes in industries? So does it make sense to spend a lot of time on validation if we know we apply the model to a different technology, so basically a different plant with different influent characteristics? So does that make sense? Yeah. So can we validate a model for future use? Okay, so I think that's a lot to think about. So when does it make sense to validate? Yeah, so the first one coming to mind is there's a new process and we want to model that, and then you have to validate, right? Because it's a new process, a new model formulation for that. process do you have to, and you should go for as many conditions as possible to validate, to make sure that the model can be widely used. Yeah. It's also, if you add a new process to an existing model, there's typically a lot of interaction with the existing processes. So you still need to make sure that the overall new model, maybe certain parts are known, has to be validated, right? So for new model developments, yes, you clearly have to, right? Important is to understand if you debate, should I validate or not? Make sure you understand the requirements for your domain of validity, which is linked to what you want to use the model for. So easy is temperature impact or seasonal load changes. So let's say there is a holiday resort and the load triples for a month, right? Then it's clear that is the critical situation. There's transition stuff going on, and you probably want to capture low load with the transition to high load, right? And you want to make sure that your model can properly predict that. So that is easy, right? So that's a special case where the models are not necessarily developed for or validated for. So yes, if you can try that. Again, a plug for the models we use these days. These engineering models implemented in simulators are very mature, are validated through thousands of simulations. And for me, the validation is through these thousands of applications, right? So we can be very happy that we have companies maintaining the models and constantly updating the default parameter sets, because let's be honest, that is not something a university could do. Yeah, so a big plug for the simulator companies. They are doing a fantastic job keeping the models up to date and also making sure that the default parameter sets are constantly updated. Okay, so just one slide on deliverables. Very important for me is documentation, right? So I want to see the calibrated and validated plant model, a description or documentation of all the inputs and settings and whatever else went in there. There will be a lot of assumptions. They have to be written out. There has to be justification for any parameter change. Don't just change up and down, say, I calibrated. There has to be some justification provided. A measure of the model prediction quality, that can be a statistic. I actually like XY plots. That gives me a nice view on how the model performed throughout the measuring range. That helps me a lot understanding model performance. If you are able to list known or potential model limitations, so that might be, oh, the database was very weak on this one, so the results have to be taken with a grain of salt. And then what I also like to see is what was the quality control procedure. I do a lot of that. So that's basically a senior review of a simulation study. So document whatever you do in your model building and simulation. All these decisions should be documented together with the underlying assumptions. I want to hear from the modeler why they did what they did. Okay, final thoughts. I leave you with a statement from Pat Coleman from the wastewater treatment modeling seminar in Mont-Saint-Anne in Quebec, and that's about why calibrate. So his statement, and he claims he heard it somewhere else, but I heard it from Pat, so I reference him in there. And he said the difference between observations and a model with default parameters is exactly what we need to understand. And I leave you with that. Thank you.
Thank you very much, Live. So we'll be opening the floor for questions. If you have any questions, just put them in the comment section and I'll read them out loud. But while that happens, I'll actually have a question myself to start with, which is something based on an experience recently. I see that some of the commercial models still have the default decay rate for OHOs, which is 0.62 from ASM1. And then ASM3, which you said is wrong, has it at zero point 0.2. And I was trying to match sludge production, but I couldn't get it with the 0.62. So first instinct would be go to the influent again to change XU, but I actually had respirometry data, so I didn't. So it wasn't really in that case, but when I dropped it to the 0.2, it actually matched the sludge production.
Yeah, so there has been a lot of research on decay. It's depending on the environmental conditions. So it's if it's aerobic, anoxic, anaerobic, I forgot. And then there are a couple more. And the decay rate depends on that, right? So and if you do that, typically you don't have to calibrate that often anymore. So with ASM1, just using one decay factor, that meant that you often had to recalibrate because we didn't recognize that there was a structural issue in the model there. So always be careful. So again, the models maintained by simulator companies, I would trust them to have the newest findings in there. So that is always the last step. First, try to understand if you missed something, right? So, for example, I mentioned that measuring wastage is a nightmare, right? So flow and TSS concentration is very often wrong. Also, if you use TSS sensors in mixed liquor, calibrating them is tricky, right? If the plant undergoes an upset, for example, the shape of the blocks may change, and that impacts the calibration of the TSS sensors, right? So be a bit careful with that. Yeah. So first try to find the error outside the biokinetic model, but in the end, so that it's valid if you have the data to support that.
All right, fair enough. Well, another question, which is what is a suitable mature model if ASM1, 2D, and 3 are a bit too old? Which I think you answered already for the commercial.
Yeah, so I would always recommend to go for a good model maintained by a group of experts, right? So that is important. There are preferences on which simulator and which model, but the funny thing is that the models are actually pretty close, right? So if you go through the details, they all have something special and little bit differences here and there, but the main processes, if you look how they are formulated and what parameters are used, they're getting closer and closer, I believe, right? So that is a good sign that the models mature. Even slightly different formulations, you will see that the parameter ranges used are getting smaller and smaller.
Another question was on the limitations of calibration and validation. So in recent years, we've seen hybrid models or data-driven models used basically to compensate for what mechanistic models cannot describe. So it says phenomena might not be captured by mechanistic model like hydraulics, oxygen gradients, simultaneous
Mm.
nitrification, denitrification. However, you mentioned tweaking parameters can lead to a wide diversity of results. Hence, my question is, where do you draw the line between your calibration process not being complete and your model not being mature enough or not being able to be mathematically accurate?
Yeah. In an ideal world, we would have mechanistic models describing everything and still run fast enough.
Yeah.
I think it depends on the application, right? So we still want to understand what's going on. We are engineers, and we should not just say, let's use data-driven models for everything or hybrids. There is still the need to understand processes, right? And that is important, mainly if I design a process. I have to understand for what I'm designing. Yeah. So for me, there is no replacement of mechanistic models. We need to understand more. We should not give up on further developing mechanistic models. On the data-driven models, there are a lot of advantages, right? So, and if you use them in optimization or control, they have a place, right? Because then it's optimization where you basically use the available data to understand interactions, and then you put an optimizer on top to find an optimum. So that is required, for example, if you have multiple objectives to decide on, right? So then you go for an optimizer, the models run faster, data-driven models run faster, and you can also use a combination of data-driven mechanistic. So for me, the most important thing is not the data-driven model itself, it's the diagnostics you put around.
Yeah.
What that means is you may be pointed to something you overlooked before, right? And it can highlight certain impacts or correlations you may have missed in the mechanistic model. But again, so if we still need mechanistic understanding to design better, right? So for operation, maybe we will see a shift towards data-driven applications, but in design, we still need to understand what we are doing.
You
I
also
hope
run
that
into a problem with instead of just data quality, and now you have data quantity also.
That's another one. So data-driven models. So that's funny, right? So we everyone heard the garbage in, garbage out,
Yeah.
right? That is true for mechanistic models, but it is not necessarily true for data-driven models. And that's quite funny to understand. So data-driven models can use bad data to still get information out if the data is consistent, right? So mechanistic model need accurate data. Data-driven models require consistent data, right? Because the first thing is you basically normalize all data and mean center. So any information on calibration is gone anyways, right? So you most important is don't touch it. Don't recalibrate your sensors if you do that.
Yeah.
So, and I think it's important to understand the use cases. But for me, it's just these are different tools, and we have to learn to use both, right? It's not one or the other, or it's not even hybrid as a mix. It's basically should focus, the discussion should focus on the application and the best tool to answer a question or solve an optimization problem, whatever. Yeah.
Uh, there's a question here. What is a good model for oxygen transfer?
I don't think we have the time to do that, but I would say write an email to Diego Rosso or Sylvie Gillo, and they can answer that question.
Diego Rosso from UC Irvine.
Yeah, or Sylvie from INRA in France.
Uh, we have another question here. If you have a new plant and historical measurements are not available, is relying on default parameters enough? Because there's a lot of oversimplification in sedimentation, sludge blanket heights and all of that. Biogas production and anaerobic digesters is more challenging in calibration. Also, sensitivity analysis
So
is important calibrations.
if it's a greenfield plant, there is no data to calibrate for. So
Exactly.
there is no calibration. So you have to start somewhere. And again, so the defaults are pretty good. Mature models, well-maintained default parameter sets that would give me the confidence to apply that. So the tricky bit is influent characteristics. If it's a greenfield plant, you are doing design anyways, right? And whatever is missing, you have to increase your safety margins, right? So that's classic engineering.
Yeah.
You work with what you've got, and as an engineer, you had to learn to deal with uncertainties, right? And you can do that in better ways than just a blanket safety margin. But if you have no additional information, then you may say we triple the volume, right? So that is a pretty safe bet.
Think there's an interesting point here when they're talking about kinetics related to denitrification are difficult to calibrate. So we see high ammonia in the effluent, high nitrate in the effluent, and there's a big gap between the real and the model, the real observations on the model. I think they're talking about when you match ammonia and then the effluent nitrate doesn't match.
Yeah. So that is a clear case where you go back to plant model setup. Don't touch the biokinetic parameters, please.
Could it be
Right. So
something with the
just
clarifier?
could be sludge blanket, could be recycle rates, could be aeration, could be not matching the DO profiles, could be bad data. There's so many things to check, but please don't touch the biokinetic parameters.
It's the last thing you resort to, basically.
Yeah, maybe
Um,
never.
maybe. Fair enough. Uh, Someone here is as a beginner in mechanistic modeling. Is there any papers, books, or guide books that can help get me started more quickly?
Yes, there's quite a handful. There is, of course, the one we wrote. I think that's a good starting point because it gives. So the focus of our work is on how to do modeling. There is a lot of descriptions of the simple models and basically an entry into more. There's a lot in our reading lists referring, but it's how to model and simulate. Um, there are other books similar to ours. There's one from WEF in North America, Manual of Practice. I forgot the number. Um, and then there are books more focused on the models themselves. So one is from Jacek Makinia. There's another IWA book with all the big names in the industry at the time, at least, on wastewater treatment. There are quite a number of books to start reading. I still believe ours is a good starting point.
Do
And
you think
again, there's
you think it's a good idea to go through the original documents of the published models, like ASM1, ASM2, ASM3, to see the model structure and learn how they behave differently? Yeah.
I have that always next to me.
Would be a good thing to go over it, or is it, do you think it's
No,
necessary, or
sure.
just
Yeah. So that I believe that the history of activate sludge models is quite helpful understanding where they came from, what drove the development, also the mistakes made. I found that fascinating. right? ASM2, for example, so missing the D at the end, which is the denitrifying PEOs, something still not completely solved, but the the researchers in South Africa missed that because of the experimental setup, right? So they didn't enrich for denitrifying PEOs just because of their experimental setup. And that's fascinating, right? So what decisions drove model development, or at least fascinating for me. I'm not sure.
Okay, there's a question here. If there's a difference in dissolved oxygen that's been observed in the between the influent and effluent, how can this be represented and calibrated within a CSTR model? I'm not sure I understand the question clearly, but maybe you do.
No,
You know,
no.
I
So
think
I
there should be a
mean,
discrepancy here.
there should be because
Yeah.
there are processes going on consuming oxygen, and there's typically also some kind of aeration going on.
Yeah.
So I'm not quite sure what the question is about.
Does anyone else have any questions? So it's a reiteration here, but if you're recommending don't touch the default parameters, and you still don't have a match in your effluent quality, what is the way to go? Do you
Repeat,
recalibrate for biokinetics, or you just basically go to the model setup again?
repeat looking for where your model may not properly be set up or into data. If you can clearly pinpoint one parameter, and that parameter may have a wider range, at one point you do that. Yeah. And there are reasons, let's say, for nitrification, there might be inhibition in the influent. I would be very careful. Most of the time, the reason is not inhibition in the influent. It's rather not properly modeling air distribution and oxygen transfer. But there are cases where you have some level of inhibition in the influent or coming with the influent. And then you can extend the model for inhibition. You can add an inhibition process, or you can basically change the nitrifier growth rate. Yeah, so that is an option. But typically, I want to have some level of justification, right?
Right.
At times, you decide to rather change biokinetic parameters, right? So, for example, if you model an oxidation ditch, you may push simultaneous nitrification, denitrification through parameters, or you model your hydrodynamics in a more complex way.
Mhm.
Right? So there are decisions. For me, the important point is you need to justify that. So you have to document that and justify, I do that because of this and that, and not just tweak 50 parameters and say, I have a perfect fit. Therefore, I didn't mention any auto calibration in that
But all of that is
presentation.
after you've exhausted everything before you got to that point. Make sure that
Yeah,
your input is correct first, anyway.
yes. And if you do, clearly justify. I want to see your underlying assumption why you think that should be changed and not something else.
Fair enough. Any other questions here? I think we're good so far. Um, 1 second. Anything Many things in the presentation seem very general and experience-based, and no real way to learn the necessary subtleties from just published materials. If you don't have someone more senior to learn them from, it is close to impossible to figure out the reasonable time. Commercial softwares aren't that amazing either, or not all of them are difficult to know which one is reliable.
Yeah, good point. I know the feeling. After I did my master thesis, I still had the understand. So that I was missing a deep understanding, and I really wanted to understand how these models work. And then I applied for an internship in Switzerland and got it. And there were experts I could ask. Right? So I was lucky, I admit that. But to be fair, so there are a lot of training courses offered. If you start a new position, make sure that you are looking for a company where there are seniors to support you and teach you how to properly apply these models. If you go for a university job or PhD study, then also make sure that you discuss that, right? And there are typically a lot of experts around, and they will guide you, right? So, but I agree, there is a lot of mentoring required. There are good publications out there, right? So I would start there, um, and yeah, then if you still want to learn more, then look out for a position where there are enough experts to teach you.
Still have some time on us, so if anyone else has any questions. I think we're set for now. Thank you very much, live. It's always a pleasure to listen to you and learn from you. And we'll see you, everyone, in the next session. Thank you.
Yeah, thanks for inviting me. Always a pleasure. And
Also,
good luck to everyone with their modeling challenges.
yeah. Thank you.